Welcome to Lab 1. Let's do some stuff with limits. So I'm going to run through the leading examples on here and just give you a little bit of insight into how this is going to work, what we're doing, why we're doing it, and hopefully that will really help as you get into the tasks that you actually have to do. So first, notice that I've already saved a copy of this in my drive. Bang, there. So now when I edit it, you can see, hey, this is actually saving changes. I've also already put my name in here. I don't know the due date. You can put that in there for yours. You can change the name of this as well. Instead of copy of Lab 1, maybe we'll do Lab 1 limits video example. Woo! You can put your name in there if you want. That makes it a little easier for me to keep track of who's who as I'm grading things. All right, let's just dive right into it. So in these leading examples, we're going to do a bunch of stuff with some limits. Some of these limits are things that we can do by hand. So I think that's worth noting because first, we can get a little bit of a practice doing them by hand, and we have a way of checking some answers here, get some familiarity with some of these concepts that we're learning about in class. But also, what we'll do is we'll work towards some stuff that we won't be able to do as easily by hand. So here's our first limit, the square root of x minus 3 over x minus 9. We're looking at what's happening as x approaches 9. And we're going to look around this point graphically to get a little graphical approximation. To do that, we're going to use this plotting library that we've got, and we're also going to use our handy-dandy NumPy library. So we'll import those first. It's going to take a little bit on this first run. Here we go. I've gone ahead and defined our function. I'm using the square root function from NumPy. So this is np.square root. Notice I'm throwing some parentheses around everything. Maybe I'll space things out to make it a little bit more readable what's happening. I've got parentheses around my numerator, parentheses around my denominator to make sure that's going to be a little bit nicer to run. Then I can set up some lists of x values. So normally we would look at x values and we'd set up this NPA range thing. That's what we've done previously. But what you're going to notice is I'm going to set up a specific one for the x values on the left and on the x values on the right. This makes sense conceptually because we think about one-sided limits a lot. So our x values on the left are going to be things that are close to but less than 9. I'm going to start at 8, count up to 9, not including 9, by 0.1s. So we'll print this out later, but this is going to be 8, 8.1, 8.2, 8.3, 8.4, etc., all the way up to 8.7, 0.8, 0.9. On the right, this is a little bit interesting in the notation that we've got. We're going to start at 10, we're going to count to 9, and in order to count backwards, we need a negative step size here. So we're going to count by negative 0.1s. So this is going to be 10, 9.9, 9.8, all the way down to 9.1 because we're not including 9. And you can see when I print those out, there we go, 8 all the way up to 8.9, 10 all the way down to 9.1. The great thing here is that now I can just go ahead and plot these things. So I'm going to plot my left x values and that function, the y values that go with the x left. I'm going to plot my right x values and the function outputs of those. So this is almost like plotting two curves. It's really the same graph, but we're splitting it into two pieces to consider each piece separately. I'm giving it a nice little title and we can show it, and look at that. We've got this weird space in the middle and you can see where it lines up. That's the space between 8.9 and 9.1. So you can kind of see like what y value it seems like we're approaching here, somewhere in there. But there's a lot of ambiguity here. Again, what I might show you is like what this actually is doing. I'm going to change it from plotting a line to just plotting the actual points. And so you can see, oh, okay, it's because of all this space in between the points. That's why we have this big empty space in the middle. We're connecting all these points with a line, but we still have that empty space in between. So what we can do is we can go ahead and change some things. But first, I want to add some more visuals. I'm going to add some more horizontal lines on here. This bit of notation right here is a little tricky. What we're doing is we're taking the last value of the right x values. So that was 8.9. This negative 1 means count from the end of the list and take the last one, and then plug that into our function. Here we're doing the same thing for the very last number on the list of x left. Remember, we counted from 10 down to 9, but not including 9, so this is 9.1. So this is f of 8.9 and f of 9.1, and we're going to plot some horizontal lines here. So what these horizontal lines are doing is it's saying our limit is probably somewhere in between here. This is the kind of measure of arbitrary closeness. Now, we're not arbitrarily close to a single y value here. Looks like there's a lot of y values that are in there, but we are certainly close to some. What we might want to do then is see where those things are. 0.1662 and 0.1671-ish. Our limit is probably in between there, right? Doesn't it look like our functions, I should say this way, are approaching the same y value that's somewhere in between those two y values? You can maybe make a guess as to where that y value actually is, but numerically this is kind of a tricky thing to do. So here what I'm doing is I'm just going to say, well, we have this extra precision with Python. Instead of counting by 0.1s, let's count by 0.0001s. So this list is like 8.0001, 8.0002, 8.0003, all the way up to 8.9999. And the x right is similarly going to count from 10 all the way down to 9.0001 because I'm changing that step size to be very precise. This code is all copy and pasted of the plot above us because we're just resaving our x left and x right as something new, but we're still calling it the same thing. So we can just copy and paste that code, and wow, look at that. Our horizontal lines seem like they've smushed down on top of each other. It looks like there's only one there. There are actually two, and you can figure out where those are by running this bit, and you can see there's a lot of precision in here. Our limit is now somewhere in between here. This gives us a better way of visually, graphically, and numerically approximating this limit. You might have an idea of what that limit is. Go ahead and compute it by hand because we can do that to see if you're correct, but we have a pretty good guess probably. And visually we can see that this is really accurate. There's not a lot of space in between here that we're missing. You can change your step size and stuff like that and see what happens, but here's the actual work with the conjugate business to show that, okay, the limit actually is a sixth. Neat. Piecewise functions are a little weird to code in Python, so I'm going to give you some help doing that. I'm using an if statement. If x is less than 4, then our function is going to be negative 3x plus 10. And otherwise, if x is greater than or equal to 4, we're going to use 2 times x minus 8. And then we have to use this weird vectorize thing. Don't worry at all about this. I will help you along the way with that. I'm going to build every piecewise function for you. Let's just run this. This is going to save g of x into the memory. So now when we call on g of x, we can see what it looks like. This is going to plot our limit around 4. And you can see there's some kind of weird stuff happening here. What I'm going to do is change that step size again, and we're going to add in those horizontal lines. Again, I'm just copy and pasting code here. I've renamed my function g, and I'm using new x left and x rights, counting from 3 up to 4 and from 5 down to 4. And this is really, really close to 4, but look at all the space in between these. These y values don't seem like they are arbitrarily close to the same thing. It looks like the left side limit is going to probably negative 2, and the right side limit seems like it's going to 0. Visually, we can see that, but we can also print it out numerically. And yeah, negative 1.9997, that looks like it's close to negative 2. We were pretty bang on there. And 0.0002, okay, yeah, we're pretty close. We could change this by adding some more zeros in here to get a little bit more accuracy in our step size. So visually, it doesn't really look like there's much difference, but when we rerun this, these numbers are going to change. They're even closer. Something went wrong. Oh, I see. Some scientific notation. Whew, that was close. So this is 0.000002, and this is negative 1.999997. I think I counted the right number of 9s there. But really close to 0, really close to negative 2. Seems like everything was working the way that we thought it was. You can dig into the code here for these horizontal lines, but that's pretty much where we're at. For the ones that you're going to do, make sure that you run this every time that you open up your lab. This is an example of a limit that we could actually figure out using the Squeeze Theorem. This is really similar to one that we have done in class, but we can look at it numerically and visually and get really good evidence that the limit is what we think it is. So go ahead and define this function x squared times sine of 2 pi x. Remember, you're going to use the trig function from the numpy package, and pi is going to come from there as well. Make sure you put multiplication signs in between the 2 and the pi and the x, all that stuff. I've given you an x left and an x right to use, so you can copy and paste those and then plot your function like we did earlier. You can copy and paste some of the horizontal line code, what you will need to change is the x values that you're looking at. So up here, this bit of code is saying this is the y value we want to plot the horizontal line at, and we want to plot it between x equals 3 and x equals 5, because that's where we were looking. We were looking around 4. In this case, we're looking around 0, so it'll probably go between like -1 and +1. So just change some of that stuff. And then I've given you this little bit of code. Once you define your function and x left and x right, that'll spit out your numerical approximations. The second example is one that we would not be able to do right now by hand. This is something that we can't access or evaluate. The first one, we could do some squeeze theorem and figure it out, but this one we can't right now. Eventually we might be able to do this. But we can at least go ahead and define the function and check out visually what's going on and see what happens. Here I'm asking you to change your step size from 0.1 to 0.01 on the next one, so you'll have 2 different plots. But visually, we should be able to get some good evidence, and maybe we'll be able to figure out what the number is that this limit actually is approaching. And then our third example is a piecewise function. Here I've defined the function for you so you don't have to do it because it's a weird one. Piecewise stuff is just weird in general, but I've gone ahead and built that thing for you. Notice this function is just not at all defined when x equals 0. It's only defined when x is less than 0 or greater than 0, but that's fine. We're looking around 0 for our limit, so it doesn't really matter. Do all the same stuff with it, see if we can visualize what's happening with these limits. Hopefully that'll go pretty well for you. I can talk more about these in office hours or in class if you'd like, but hopefully this video will serve as a pretty nice introduction to get you running with this lab. Good luck everybody, and let me know if you have any questions.